So just an outline of the presentation. We'll start with an overview with some project background before moving into performance of the thermal pretreatment system. So we'll talk a little bit more about, again, the background of the project, but in addition to thermal desalination, we also tested membrane desalination. So there was a separate pretreatment process associated with that system that we'll talk about next. And then finally, we'll wrap it up with some key conclusions. Right, so starting with background or overview of the problem here. So where beneficial reuse comes into play in the grand scheme of things. So as I'm sure most people on this call are aware, produced water and beneficial reuse of produced water in particular presents a unique opportunity to tap into a new freshwater resource. So this is something that, rarely you get the opportunity to take advantage of here. And so, right now we're at greater than 20 million barrels per day of produced water and only increasing. So this could be a win for, again, all parties involved if done properly. So starting with communities, producing more fresh water from produced water can improve local water securities, and then also conserve the aquifers that are stressed for local use. It also provides a drought-resilient supply of fresh water for non-potable uses. So as we'll talk about next here on the industry side, more availability of fresh water means that you are able to minimize the usage of fresh water, again, from the local aquifers. It also means that you have a cost-competitive alternative to deep well injection of produced water, which is the primary way that produced water is handled to date. And then finally, the fresh water that's produced, of course, can be treated to different levels depending on what the end use application is. So fit for purpose processes can encourage industry growth. And so, data centers are a very popular topic, but also power is another need in the region. And so can help to close some of those gaps as well to increase the industry in the region. On the environmental side, there's also the opportunity to discharge this new fresh water from produced water to surface waters that have been at low levels in recent years. And so it can be a boon again to the local region, recharging the surface waters. Less injection of produced water also means that you reduce the seismicity risk, which we've also seen tick up in recent years in the region. And then finally, just wanting to note here that through rigorous analysis of the polished desalinated produced water, we can be good stewards to the environment. So making sure that we properly, identify all of the contaminants in that water and their toxicity risks that they would pose. So through wet testing, we're able to identify again, which contaminant or if contaminants are present in levels that can be toxic to aquatic life. And then through non-targeted analysis, we're able to identify any components that are not part of your standard targeted analysis lists to better quantify, again, what we're putting into these surface waters potentially. And then finally, by introducing new industry into the region, we can foster economic development. So job growth and investment into new industries could be, again, a major boon for the region. And another application here, supporting local agriculture through use of this desalinated water as irrigation water for non-consumptive crops. On the next slide here, I'm going to transition now into talking a bit more about the pilot project. So the goal of this project is to develop cost-effective and scalable methods for treating produced water for beneficial reuse. So this is part of a joint industry project that we undertook previously as Aris Water, now as Western Midstream, with the 4 partners listed here. So that's Chevron, ConocoPhillips, Qatar Energy, and ExxonMobil. The pilot plant that we deployed was located in the Delaware Basin and was operated by Western Midstream. And here on this slide, you can see a picture of that pilot plant. So what you're looking at here includes not just the desalination equipment, but all of your pretreatment equipment as well as post-treatment. So this was an integrated pilot plant. So meaning we had continuous operation and flow through all three sections of the plant: pretreatment, desalination, and post-treatment. We began operations in the fall of 2023. And that continued until last summer. So pilot operations have completed for that phase of the project. And during that time period, we did collect over 50,000 water quality data points across the system via commercial lab analysis. And so that's in addition to thousands of data points that we collected through field analysis as well. During this time period, we also did test multiple thermal and membrane desalination technologies. So in this presentation, we'll be focusing on the pretreatment systems that were associated with the thermal technologies, as well as the pretreatment system associated with the membrane desalination systems. So now, before moving into some treatment results from the pretreatment systems, I just want to provide a little bit of context as to the quality of the water that we were seeing during the course of piloting. So this is showing our raw produced water TDS, or total dissolved solids. And this is a time series going from March of 2024 through May of 2025. And what you'll see here is that, first of all, it's very high salinity, of course, so greater than 100,000 milligrams per liter, and as high as 180,000 milligrams per liter. So much saltier than seawater, 3 to 5 times greater, in fact. And so our target here during this pilot was to remove more than 99% of that salt content from the water. And then just for reference here, again, our target is to produce a finished water, or a polished desalinated treated water in the range of drinking water salinity, so less than 500 milligrams per liter. And so with all this variability and all of this salt content, it's important to design a pretreatment system that can adapt or be robust to changes in feed water quality. That way you're able to maintain your finished water quality that you're looking for. And so next here, along with the variability in salinity, you'll also have variability in various other constituents of the produced water that present different challenges for thermal desal systems and membrane desalination systems. So these challenges, while they are universal to some degree, the impact that they have on the desalination process is dependent on the process being used. So here, really just listing through some of the various challenges that you would see across different groups of constituents. And so really starting with alkalinity and hardness here at the top, you do have challenges associated with calcium carbonate formation in thermal desalination systems due to the reverse solubility trend that you see with calcium carbonate at high temperature. So that's not as great of an issue for a membrane desalination system, which operates at ambient temperature. However, you still have potential for scale formation if you don't have proper scaling control, which can lead to reduction in your flux of your membranes and therefore less production of permeate. In the case of the thermal system, of course, if you have calcium carbonate precipitation, this can lead to scale formation on your heat exchanger, which reduces the heat transfer surface available and therefore also reduces your efficiency of that process. With respect to biology, both systems can be sensitive to this, and in particular on the thermal system, fouling of the heat exchanger leads to reduced heat transfer, but you can also have corrosion issues potentially with biological activity. In a membrane system, too, you would have issues of biofouling that can reduce your membrane flux, as that membrane surface, as we'll talk about in a second here, is very susceptible to any sort of foulant or scale deposition that could block the available area for water to pass through. On the organic side, the contaminants of concern for us at the start of this project were free and dispersed hydrocarbons. So with a thermal system, this can manifest in foaming issues for one, which can be managed with defoamer addition. But you also have issues related to the volatile organic compounds, which can carry over with the distillate into your post-treatment or into your finished water potentially. So that is something that you have to pay special mind to with a thermal distillation process. And again, in addition to fouling of your heat exchanger. With membrane desalination, these hydrocarbons can organically foul the membranes, again, leading to loss of flux. But you can also get irreversible fouling. So this is fouling that can't be cleaned off of those membranes and leads to a permanent loss of flux. So really reduces the productivity of those membranes as well as the lifespan. So leads to increased costs. For sparingly soluble salts, this is similar to what we see with alkalinity and hardness in that if you don't have proper control of scale formation specific to some of these salts, you can begin to see scale deposition either on heat exchanger surfaces for thermal systems or on the membranes for membrane desalination. So in either case, reduced productivity of those systems can occur. And then finally, with total suspended solids, these can act as nucleation sites for scale formation and also can erode your equipment. So in particular, on a membrane system, this can be quite damaging to the membrane surface. So abrasion can form mechanical tears in those membranes and lead to essentially short circuiting of that feed solution and leading to loss of rejection and increase in flux. Right. So now just going to give a couple of high-level descriptions of the desalination technologies that were tested, and then we'll move into understanding the pretreatment that was tested and the results that we received. So on the membrane side of things here on the left, you're seeing here an image of a single membrane element. So this is essentially a semi-permeable flat sheet that's rolled in a spiral. And you can see that membrane consists of multiple layers. So on the surface, you have a feed water carrier. So that shows up as the black mesh here in this image, which allows the feed water to be distributed across the membrane as it flows across. From there, you have your semi-permeable membrane layer, which allows your fresh water to pass through. And this is where the salt rejection occurs. And then in the middle here, you have a green sheet as depicted, which is a permeate carrier. So this helps to carry your permeate to the center of that spiral. You can see a perforated product tube, as it's labeled here, which collects your permeate, and then it is pumped out and collected downstream. So by the time the feed exits from one end of this spiral to the other, it's been concentrated, and you have a brine, which now has a higher concentration factor for all of the salts that have been rejected. So as you progress through a desalination system, you really have to consider what that concentration of salts will be at the final stage of your membrane system, as that's where your scaling potential is the highest. And so as mentioned, these membranes are actually very susceptible to scaling and fouling more so than a thermal distillation system. And so extra measures have to be put into place on your pretreatment side to be able to manage and mitigate scale and fouling formation on these membranes. But on the flip side, the advantage to membranes and why we're so interested in looking at them is that they're much less energy intensive than a thermal distillation system. So conversely, with thermal distillation as pictured on the right here, it's a very simple and robust technology that requires a much lesser degree of pretreatment. So as we walk through the treatment processes, you will notice that there were more steps in the pretreatment system for the membrane desalination than there were for the thermal distillation system. All right, so with that background out of the way, I'm going to now transition to talking about the thermal pretreatment system performance. Right, so here we have a review of the water quality that was received during the thermal distillation testing in this pilot. And so you can see the first table on the bottom left here shows our raw produced water quality. So what we expected to see based on testing that was performed a year prior to the start of piloting, and then the maximum levels that we actually observed during the test period. So you can see right off the bat that with respect to total dissolved solids, we were seeing higher TDS than anticipated, which, as mentioned before, can have some implications on some of your other contaminants as you're concentrating the water. But just high level, what our needs were with the pretreatment system for the thermal desalination system were removal of total suspended solids and oils, as well as iron and some alkalinity. So the reason for this, again, is just to minimize the amount of abrasion or erosion of your equipment that you would see from your suspended solids, and also to minimize the risk of organic fouling and scale formation on the heat exchangers. And so you can see here also on the right-hand side what our targets were on the pretreated water as well as the final desalinated water out of the thermal system. And so we'll take a look at those a little more in depth in later slides here. So here's our block flow diagram for the pretreatment process that we employed on the thermal desal system. So the raw produced water flowed through a flotation unit process here that targeted really removal of your turbidity, iron, and your hexane extractable material. So on the turbidity side, we're targeting less than 10 NTU. For iron, less than 2 ppm, and then greater than 90% of your HEM removal. Following the flotation step, we had a coarse filtration system, which included a media that was that had an affinity for hydrocarbons. And so here we were targeting TOC of less than 50 milligrams per liter, as well as a turbidity of less than 3 NTU. So some polishing on the organics and on the solids. And then finally, degasification was employed for reduction of the alkalinity with a target of 50% removal. The goal here being to reduce the scaling potential from calcium carbonate. And after the degasifier, it then went to the thermal distillation system for desalination. So first, we want to show some of the results that we achieved here on the iron removal aspect. So on the graph on the right-hand side here, you can see the KPI that I just stated is shown with that red horizontal line, less than 2 milligrams per liter. And we're looking at the average levels of total iron exiting your flotation system as well as the filtration system. And so what we observed in the data was that we were consistently able to meet our KPI here. And on average, you can see we were well below that 2 milligram per liter target by the time we finished filtration treatment. And what this told us is that our approach of doing bulk removal with an oxidizer and flotation was effective. And this is something that is commonly employed in recycling sites around the Permian Basin. So this was nothing new, but seeing about 90% removal of the iron through the flotation step. And then additional removal of the residual ferric iron after that flotation treatment was achieved through the filtration. So really that filtration unit was effective as a sort of insurance policy whenever there were any upsets in the flotation treatment, whether that be due to maintenance or other systems failing due to it being a pilot system. And so we really saw that we got very good performance out of that filter there to maintain our iron levels well below our KPI. So next, looking at turbidity, we were wanting to see how the flotation and filtration systems could achieve those KPIs shown there of 10 NTU and 3 NTU respectively. And we did see in this particular case, 91% reduction achieved through that first pretreatment step. And again, having that filter as the insurance policy or the backup for cases where we had upsets in the flotation system upstream. But in particular, with a thermal system, as mentioned, a thermal desalination system, they are much less sensitive to the particulates that are in the feed stream or the pre-treated water stream. And so for us, this level of treatment was sufficient to ensure that that system would be protected. All right, now moving over to alkalinity performance. So this degasification process incorporated acidification upstream in order to convert the alkalinity to carbon dioxide. And so the feed pH is strongly, the removal of your alkalinity as CO2 is strongly dependent on the feed pH that you're achieving. And so you'll see here where we had no pH adjustment through the filtration product, we really saw no change in our alkalinity as expected. And then that acidification step happened after the filtration. So reducing that pH to weak acid levels did facilitate consistently that removal of alkalinity. So you can see our KPI of 50%, we were just below that on average at 49% removal. And so just want to dig in a little bit deeper on this particular system's performance to illustrate the importance of that feed pH on removal. And so this graph here just breaks it down, showing a collection of samples through commercial lab analysis that show the alkalinity change from the feed to the product of the degasifier. And so the blue bars here represent the feed stream. The red bars are the product stream. And plotted overlapping on these bar graphs is a line graph showing your pH of the feed. So that's on the secondary y-axis there. And what you'll notice here is in the first month and a half or so of operation, we had very inconsistent control of that feed pH. So that initial sample collected in April here, you'll see essentially we had no pH adjustment at that point in time, and we saw no change in our alkalinity. However, after improving a bit on that pH control, you can see at around a level of 5.5 pH, that reduction of alkalinity jumps to about 40 to 43%. So an improvement, but still not quite on target. We had a bit of a mishap in mid-May here. You'll see that we over-adjusted our pH to just over 4.1. And at that point in time, you also see significant removal of that alkalinity, so 98% removal. But after making some adjustments to our pH control scheme, we did achieve much more consistent pH in the latter half here of the operational period. And you can see that in the end, as long as we keep the pH below 5.3, we're able to maintain that alkalinity removal of 50% that we were targeting. All right, and then looking at TOC removal. So here, plotted on the right, we have the TOC across the pretreatment system, but we've also included the distillate stream at the end. So we just wanted to illustrate the characterization of TOC removal here. So our target KPI was less than 50 milligrams per liter from the filtration product. You can see here that we really did not, we weren't able to achieve that on average here. What we did see is that the flotation and filtration steps upstream did show removal of free and dispersed hydrocarbons. So about 3.6 milligrams per liter and 1.9 milligrams per liter through those first two steps respectively. And then as we treated the water through the degasifier, we saw a significant reduction there down to just over 30 milligrams per liter of TOC. So this suggests that majority of that removal is due to volatile organic compounds that remained in the water being stripped with the air through the degasifier. However, the fact that we don't see much change from the degasifier product to the distillate stream suggests that we have significant levels of carryover there that can be attributed to water-soluble organics primarily. And so we wanted to dig a little deeper into the composition of that TOC, which we found to be really important in these pretreatment systems, not just knowing the general TOC. To better understand, what we would need to do to further reduce those TOC levels in the polished desalinated produced water. So here we're looking at a breakdown in the raw produced water and the distillate of our TOC, and really just two main categories shown here. Very simple: acetic acid and everything else. So the acetic acid in particular showed to be the primary component of the TOC, both in the raw produced water and in the distillate. So you can see in raw produced water, it made up 71% of the TOC. And in the distillate, that increased to 84%, again, due to the removal of the free and dispersed oils, as well as some of the VOCs. And so, again, acetic acid is water soluble. So as a result, during the distillation process, it does pass through significantly into the distillate, as we're seeing here. But you do see that we had some partial removal, going from 41.9 milligrams per liter to 25.7 milligrams per liter. And we can attribute that primarily to the degasifier due to the change in TOC levels that we saw there. If you wanted to achieve lower levels in this particular type of desalination system on your TOC, then you would need to incorporate additional pretreatment or post-treatment that is targeted more towards acetic acid or other water-soluble organics. So that's not something that we had as part of this particular system. And we didn't find that the acetic acid otherwise impacted the treatment scheme in any negative way, other than, again, having higher levels of TOC remaining in that distillate. Right, so with that, I'm going to hand it off to Mohammad, and he's going to walk us through the membrane pretreatment system performance.
Thanks, Javier. As Javier mentioned, I'm going to take you guys through some of our pretreatment performance that we saw on our membrane system. Javier, the next slide. So similar to the same slide that we saw with thermal, this is kind of the expected raw water that we based off of some sampling prior to the initiation of these pilots. And then on the first chart here on the right-hand side, we have the max that we saw. So some of the bigger differences here are considerably more TDS than we expected, with a max of 180,000 milligrams per liter. And then we also had quite a bit of total suspended solids, higher than we expected, about 5,700 compared to what we were thinking around the 100 to 200 range. So we expected that this would be pre-treated to pretty low levels. We were expecting pre-treatment to drop this to not really take too much of the TDS, and that we would see the majority of the TDS be taken out through the desalination process. But we do expect to remove a considerable amount of the total suspended solids through the pretreatment. So up top, we have some of the pretreatment needs for membrane. So membranes is a little bit different than thermal. So we still need to remove TSS and colloidal matter similar to thermal, but we also need to pay specifically to the hydrocarbons, especially some of these hydrocarbons that can foul up the membranes permanently. And additionally, we still need removal of inorganic and organic colloids and foulants. All right, I think next slide. So here's our block flow diagram for membrane pretreatment. It's similar to thermal, but we have two additional steps here. So the flotation and the filtration are similar to what we saw with thermal. However, we add an additional step between filtration and degasification, which is fine filtration. The purpose of fine filtration is specifically to remove some more of the turbidity, remove some of those inorganics that are going to have potential to foul, and then specifically to remove some of that organic carbon and BTEX, which can harm the membranes. So that's one of the main differences. And then after degasification, we also add a pretreatment polishing step. The main purpose of this pretreatment polishing step was to help remove, again, some of these organics specifically targeted at iron and manganese. Inorganics simply because these were two of the constituents that we identified as having high potential for fouling on the membranes. So we wanted to ensure that we had these inorganics at a pretty low level prior to entering the membrane desalination plant. Now, for the other three steps that are similar between thermal and membrane, the flotation, filtration, and degasification, we had very similar KPIs to the thermal unit. But through fine filtration and pretreatment polishing, we wanted to remove greater than 95% of our BTEX. And additionally, we wanted to drop our TOC to below 30 milligrams per liter and also reduce turbidity to less than 1. And then overall, we wanted to see manganese at below 0.2 milligrams per liter and then iron at 0.5 milligrams per liter also. So iron removal showed a similar trend to what we saw with thermal. So we see and just for clarification, the y-axis on this graph is on log scale. So we see there's considerably higher amounts of iron in the raw produced compared to what we have at the end in the fine filtration. So we were able to consistently reduce iron to below our target KPI in the filtration effluent. So our target KPI, again, was less than 0.1 milligrams per liter, and we were consistently able to reach that limit in our fine filtration product. So, but the bulk removal was achieved through the flotation due to oxidation and flocculation. So we see about a 92% removal from the raw produced to the flotation product. And then the purpose of us having this removal of iron, again, is due to the membrane sensitivity to this inorganic scaling. So, with membranes, the surface area, our active surface area, is one of the most important concepts for high flux. So your surface area is directly related to your flux. So any kind of scaling that we have on the membrane surface is going to reduce the flux and reduce the performance of our system overall. So again, iron and manganese are two of the inorganics that we were quite worried about. Or we wanted to target, I don't want to say worried, but target to remove so that we didn't have any problems with this later on in our membrane system. So we need a little bit greater iron removal than we saw in thermal system, just because the thermal system is a little bit more robust to handling these deposits, whereas the membrane system is a little more sensitive. But overall, we see a greater than 99.7% removal of iron through our pretreatment for the membrane system. So manganese was another one of the inorganics that we really wanted to target. So here we see in the graph on the right-hand side that we have the raw produced, we have what we get out of our fine filtration product, and then our pretreatment polishing product. So we can see that between the raw produced all the way to the fine filtration product, so the majority of the pretreatment train, we don't really see much removal of manganese. You see a slight increase in manganese between raw produced and fine filtration, but we consider that to be just within the typical standard kind of variation that you're going to see in sampling. So not that we're adding any manganese through the system, it's just the sampling. So our goal was to have a KPI or a level of 0.5 milligrams per liter or less of manganese coming outside the fine filtration system. That wasn't achieved. Not able to really get that manganese oxidized just due to the long induction time for dissolved manganese to precipitate. So it just takes too long, and by the time we get through the fine filtration, it still hasn't fully oxidized, so we're still seeing some of that dissolved. So the pretreatment polishing product is kind of the final step prior to entering the membrane system. So we saw really good removal of manganese here. So we're hitting our KPI of 0.2 milligrams per liter. And this is due to the pretreatment polishing having a catalyzed oxidation of manganese. So a really targeted removal of manganese, and it allows for the manganese to precipitate much faster and therefore be rejected or removed more efficiently. All right, alkalinity removal, similar to thermal, is one of the key concepts here. We want to reduce overall carbonate species so that we have less carbonate scalants forming in the membrane system, especially as we concentrate. So we saw slight decreases through the beginning of the filtration pretreatment train until fine filtration, but we see again the majority of the removal from the degasifier. The membrane pilot was conducted after the thermal pilot, so we kind of took some of those learnings that we got from the thermal pilot of the pH control and the optimum pH being below 5.3 and applied it to the membrane system. So we already kind of had that dialed in, so to speak. So we can see that we consistently hit that 50% or greater reduction in alkalinity from the going through the degasifier. So again, this confirms that we have good acidification, and then we also have good gas dripping in this system. And then again, for membrane unit, the lower alkalinity upstream is important, so we can reduce the potential of scaling of carbonate salts. Carbonate salts are really insoluble. So one of the again targeted removals was the carbonates in with the inorganic and organic constituents. So turbidity reduction, here we took it as a stepwise function, as can be seen with the three different KPIs that we have. So we have the KPI for our flotation step, which is below 10, and we consistently hit that. So less than 10 NTUs. The next KPI that we had was below 3 NTUs for the filtration step. And again, we consistently hit that. And then we see a really good removal of turbidity through our fine filtration, where our KPI was less than 1 NTU, and we were quite below that KPI majority of the time. So we took this in a tiered step. So, remove some of the turbidity in one step and so on and so on, so that we don't have any problems with fouling or maybe getting clogged and increases in DP in some of these pre-treatment processes. So overall, good trend of decreasing. And again, similar to the previous graphs, this one has a log scale on the y-axis, just to point that out. We again met our KPIs consistently, and then this includes, so this allows us to have very low turbidity entering the membrane system. Again, that's very important so that we can have lower particulate and colloidal fouling on the membrane surface. Again, the whole goal here is to try to keep those membrane surfaces as clean and pristine as possible.
I just want to mention really quickly here, how important the removal of colloidal material was to the operation of the membrane system. So it's not listed as one of our KPIs here, but we also had online silt density index measurements, SDI, to kind of have as a verification, again, that our turbidity and our colloidal particulates were low in the water that was entering the membrane system.
TOC removal, we see the same story that we saw with the thermal, where a good portion of our TOC throughout the pre-treatment is made up of acetic acid. So we see moderate removal of the TOC, going from the raw produce to the fine filtration, flotation, then fine filtration, and then eventually to the pre-treatment polisher. But it kind of levels off towards the end of that pre-treatment train. We don't really see a ton of removal. We aren't really able to hit our KPIs. We're slightly above them. So our filtration KPI of having a less than 50 milligrams per liter, we were slightly above that, around like 53 on average. And then for our fine filtration KPI, we wanted less than 30, and we were more so above 40 for that. Again, it was due to the acetic acid and not having a targeted process like a deaerator in the pretreatment process that was targeting the acetic acid. Uh, Again, acetic acid super has a low molecular weight and highly soluble, so it's able to pass through a lot of these steps uh, and stay within the water until we get to the membrane process. But the difference here between the membrane process and the thermal process is during the thermal process we saw carryover of acetic acid into the distillate. We saw really good rejection of the acetic acid through the membrane process. So you can see here in the permeate that we got it all the way down to sub 5 levels, sub 5 milligram per liter levels, and a lot of times to basically non-detect levels are the detection limit of the commercial lab. So uh, really good removal of acetic acid at neutral pHs through the membrane system. So this eliminates any need for a deaerator or any other targeted pre-treatment or post-treatment process within the membrane system. So you would still need that with the thermal just because you have the carryover in the thermal distillate. But as far as the membrane system goes, membrane system desalination showed really good removal of the acetic acid. So no additional step would probably be necessary. So we kind of touched on this in the beginning of this membrane section is like BTEX removal was one of our targets here. And one of the main reasons that we added this fine filtration step to the pretreatment train for the membrane process. Again, these organics can foul the membranes downstream, and then additionally they can cause permanent or irreversible damage. So it was very important that we try to control the BTEX prior to getting to the membrane process. So this bar chart shows that we have pretty good removal initially through flotation. Again, we're removing the dissolved and emulsified hydrocarbons through flotation. We don't really see too much removal between flotation and then the filtration product. So the filtration product or the filtration system does have a small amount of organic removal, but we really see a large amount of organic removal between occurring in the fine filtration product. So the fine filtration system has powder activated carbon on top of the filters, so it allows some of the constituents to be absorbed. What we saw when we broke down the BTEX, so we actually analyzed each of the BTEX constituents, the benzene, the toluene, ethyl benzene, and xylene separately. And the values you see here on the chart are those summed together. We saw that typically benzene and toluene were a little bit higher in our systems compared to the other two throughout the pretreatment. So through the fine filtration system, we actually get the ethylbenzene and xylene to a consistently non-detect level. However, the benzene and toluene, which had higher concentrations, kind of saturate the pack, and then we see a breakthrough. So that's why we still see some BTEX leaving the fine filtration product. So one of the challenges that we had in this membrane pretreatment process was field measurement of manganese. So having a reliable way of us to measure these manganese. Again, manganese is that one of those target inorganics that we were worried about kind of fouling the membranes downstream. So we wanted to have a field method of measuring it. Takes a while to get commercial lab results back. So real time, what is our manganese so that we can ensure that we're not having any consistent or considerable amounts pass through to the membrane system. So initially we tried using the hack analysis, the PAN method, and it showed inconsistent results. So here on the right in the graph, the hollowed out symbols are the field uh, results, and then the solid symbols are what we got from the commercial lab. So you can see here for the same samples, the one that tested in the field versus those sent to the commercial lab, we're seeing consistently higher. And the key thing here is to show that our field pre-treatment polished product, the triangles, never hit our KPIs, whereas when we send to the commercial lab, they hit our KPIs. So we identified this as being a problem or an area that we needed to improve on so we can get more consistent field results and understand what our real manganese was. So our solution to this was we were able to procure a AAS, atomic absorption spectrometry setup and this allowed us to get more accurate manganese results in the field. So we had, which aligned a lot more closely to the commercial lab analysis due to the higher accuracy and more sensitive detection limits. So this was just one of the problems that we had that we were able to overcome through the pilot.
Yeah, I just want to comment that that's a common challenge that we faced with respect to the produced water on the pretreatment side of things is the high salinity of those samples make it very difficult with some of these field methods to get accurate results. Even with analytical methods in the commercial lab, there's challenges due to the high salinity, but unfortunately with this particular field method for manganese from Hawk, as Mohammad mentioned, we weren't really able to overcome those issues, even with dilution.
So one of the other operational challenges that we had here was biological activity. So what we did was we monitored ATP across the pretreatment train to identify if there was any elevated biological activity, particularly around the sodium bisulfate dosing. So initially, we had the sodium bisulfate dosing ahead of the membrane pre-filters, which promoted rapid microbial growth and filter fouling. So to correct this, we moved that SBS dosing downstream of the cartridge filters. And then additionally, we implemented a DBMPA dosing regimen so we can effectively control biofouling. On the right-hand side, this is just a graph showing the ATP that we saw at 3 sampling locations. So the flotation product, filtration product, and then the fine filtration product. Some of the key points of this graph is that you can see that at some points we have ATP at higher than 9,000 picograms per milliliter. And then on the other side, what I want to point out is that we see that ATP sometimes increases as we go down the train. So even though we don't see the ATP or biological activity maybe in the flotation product, which is one of the first steps, we do see it in the filtration product and the fine filtration product. So the increased number of unit operations that we saw with this membrane pretreatment process, more locations, holding tanks, more pretreatment units, gives more interfaces or stagnant zones, low flow areas that can act as biological hotspots, allowing for the biological activity to proliferate. So this amplifies the risk of biological control if we don't have any kind of regimen applied. Again, we were kind of able to control this with some DBMPA dosing on a consistent basis. And then the last thing I wanted to point out here, if you look at the graph again, we really saw these elevated levels of ATP kind of in the hotter months. As you see, when we get to the end of October, early November, it kind of dies down in the colder months. And so, again, adjusting that regimen to accommodate for the hotter months where we're going to see the higher biological activity, and then kind of laying off it when we see in the colder months, again, things that we were able to learn and challenges that we were able to overcome during this pilot. All right, so just some key conclusions that we came out of this. So there's 4 really good key conclusions that we have here. So pilot scale testing that demonstrated that we can clean this produced water, or we can effectively pre-treat this produced water for beneficial reuse when we align with the selected desalination technology. So again, for example, with the membrane process, having that additional fine filtration step to remove some more of the organics and BTEX and turbidity, and then having that polishing step to help remove some more of those inorganics to reduce them to levels that are suitable for the membrane process. Number 2, the thermal pretreatment proved robust for achieving strong iron turbidity and alkalinity removal. However, we did see that some of those highly soluble water soluble organics, particularly acetic acid, were able to pass through and pass through and stay in the distillate. So we would need some additional polishing to lower the TOC levels, either in the pre-treatment or post-treatment of the thermal system. For example, adding a deaeration unit. Um, the membrane pretreatment had to be more stringent as far as iron and turbidity KPIs go, and also with BTEX, just because of the potential for scaling and fouling of the membranes. Uh, we needed just tighter operational control pretty much throughout the pretreatment to manage the breakthroughs, biofouling, and any other the inorganics. And then number four, successful long-term operation of desalination systems for beneficial reuse depends on consistent pH control, biological management, and then understanding the organic speciation, not just bulk TOC levels. We did notice through these pilots is that the organic makeup of the produced water slightly changes as different producers are sending the water to the plant, and then additionally, these producers are also changing the organic kind of the surfactants and anti-scaling or anti-corrosion inhibitors that they're adding to their water. So we see that the organic changes. So we need to be able to handle a wide range of organic speciations.
All right, that's what we had. Thank you, everyone, and we'll take any questions.
Awesome. Thanks so much, Javier. Thanks so much, Mohammed. Definitely a couple of questions in the chat here. And so one of the first ones that came up was, how are you measuring BTEX?
Yeah, BTEX was being performed by commercial lab analysis. So we were using the EPA method, or they were using the EPA method for BTEX. And then, as Mohammed mentioned, we were just taking the sum of the individual BTEX components there to present as a total BTEX value.
Great. And I think a follow-up question from the same person was asking, for TOC, are you measuring the non-purgeable organic carbon as well?
We were not measuring the non-purgeable organic carbon specifically, just the TOC.
Very good. I had put a couple of questions in there. These are a little bit more complex questions. And so I was very curious, seeing the acetic acid in your feed, is that something that you would expect to be pretty consistent in a feed water? And I guess the bigger question is, would you expect over a long period of time the feed water to change considerably enough where it impacted your treatment train or your treatment process choices?
Yeah, I think we did see it consistently here over the course of the couple of years of piloting at this location, and we didn't exactly specify, excuse me, where the water was coming from, but it was off of a pipeline that was fed from multiple wells. So I think about 6 to 8 wells at any point in time. So it does suggest that at least in that particular region of the basin, there is significant acetic acid levels. I'm not too certain. I can't comment too much as to if you would expect to see it. If you go to a different part of the basin there, but yeah, I would say we would expect to see it at least in this location moving forward. And then as far as how we would tailor the treatment process, I think really it comes down to, again, are you using a thermal desalination system or a membrane desalination system? As Mohammed showed there, we got very good rejection of acetic acid when you operate a membrane system at neutral pH, to the point where you really don't need any sort of additional pretreatment or post-treatment for that specifically. Still, we did include some post-treatment for polar organic compounds on the membrane desalination system, just to account for any other organics that could have gotten through. So I think it's always it would be a good practice to maintain different barriers of protection downstream of your desalination system. But certainly for a thermal system, you would absolutely need to have something in place if your target is to reduce those TOC levels. So I think we might have mentioned it, but we really didn't see any adverse effects to the treatment processes with having that acetic acid present. But one point that we had discussed is, even if acetic acid itself isn't harmful to the process and isn't toxic, it can still contribute to BOD in surface waters. So could be something to address there.
No, definitely very, very good point. Um, let's see. Another question is what type of membrane was able to show such good performance of acid removal in the pretreatment step?
Uh, Sorry, can you repeat that question?
Yeah, it says what type of membrane was able to show such good acid removal in the pretreatment?
So I guess I don't quite understand what's meant by acid removal.
Yeah, not sure either. Well, maybe they can. Oh, sorry, acetic acid removal.
Ah, okay, okay, yeah. So for the acetic acid removal, well, I guess to talk a little bit about the membrane desal system, it was a three-pass system. So it's osmotically assisted RO, meaning we're accepting high salinity brine in the feed stage and using looser membranes to allow uh, desalination to occur at seawater RO pressures. So essentially, what we're seeing is that at neutral pH, through these leaky RO membranes, we are getting some rejection of that acetic acid, but we also saw the same in the second pass, which is more of a traditional seawater RO. So by the time we, treat the water through these three passes, you see that acetic acid levels step down, and as Mohammad showed, go to near or at non-detect levels in the final permeate.
Very good. Yeah, I was actually really happy to see such nice rejection there. Couple other, we had Zahi commenting here on just a TOC loading. Did you guys see any sort of flux decline on the membrane system over time that would indicate foul?
Yeah, yeah, certainly. So I guess that's a good question that we can comment on with respect to what actually did we see in terms of impact on flux with the membranes. So we actually, just before I get to the organics, I'll just state that we were really quite pleased with the performance with respect to inorganic removal during membrane autopsy and cleaning. We really didn't see many signs of significant scale formation that was impacting performance. It was really more on the organic side and biofouling in particular that did lead to loss of flux. And so we did see that about well, some percentage of that could be regained through cleaning of the membranes. But one reason why we've included the irreversible fouling here is that we did find that depending on the composition of those organics that the membranes come in contact with, we did have some irreversible fouling as well that they contributed to.
Very difficult water to treat, so no big surprise there, but it looks like from your performance, you guys did a pretty decent job of controlling that for the most part to get those good results. Um, See, a couple of questions here, one from me, one from Brian, just on this general idea of, what were the rough costs for the membrane versus the thermal? There's that hypothesis, right, that, the membranes use less energy, so they could be theoretically cost effective, but you've got a little bit more pretreatment up front for those. I think we're assuming a little bit more chemical consumption through the biocides and maybe anti-scalants versus the thermal, but on the thermal process, you probably have more post-treatment. And so, were there any conclusive findings you can share kind of on cost in comparison between the membrane and the thermal?
Yeah, I can't share anything detailed, unfortunately, but just very high level. I mean, we did find that energy cost was significant for the thermal system. So much so that even with the additional pretreatment and chemical usage for the membrane system, the cost still came out much more favorably to the thermal.
Very cool. Yeah, and I know there's some sensitive information in there, so don't want to dig too much deeper. But um, maybe one follow-up question on that. If you could wave a magic wand and have any single improvement for the membranes, what would it be? It's my understanding that not always, commercial availability could be low, but do they need to be tailored a little bit more to improve performance, longevity, or would you even look at upstream processes to make that treatment trade more effective?
Yeah, I think that last point you made there is exactly one of the things that we're looking at here in the next phase of piloting is how to make that pretreatment process a bit more effective and robust with respect to the organic fouling and specifically irreversible organic fouling. So that's certainly something. I think another challenge that we've found going through this process is just the availability of these membranes commercially. So this is R&D, so thankfully we were able to get our hands on some membranes that were able to perform and generate this data. But at the same time, the development or the available products out there are limited. So I think that's something that we want to see obviously develop here in the short term so that it becomes more cost competitive as well.
Awesome. Thank you, Javier. Last one for me, and folks, please pepper our presenters here with questions in the chat. You had mentioned in the beginning that manganese was a little bit tough to measure due to the matrix. Were you seeing anything that was difficult to measure, or that you wish you had more, I guess, inline or real-time monitoring for on the back end of either the thermal or the membrane-based process that would help with the operations?
That's a good question. Mohammed, do you want to take that one?
I don't know. I thought the same thing. That's a good question as far as post treatment goes.
This is a question coming from a recent DOE workshop, and there are, I think, a lot of our attendees were at that in Houston after PWS. But DOE is really curious on this of where can they help, especially on the R&D front. And this topic came up because theoretically, if you can get some sort of real-time sensor in there to measure something, you can automate part of your system to at least optimize for that or ensure that you're removing it. But one of those big questions is what would you want to measure?
Yeah, I mean, I can jump in and just say, like, I think on the brine side, it's very difficult to have instruments that, or to find instruments that perform reliably without breaking down. So we did have some challenges with oil and grease, for instance, trying to measure that online. So, having to resort to more manual, benchtop methods to do that analysis for much of the time. And I think, again, manganese, like you mentioned, was a bit of a pain point for us. So having, again, just instruments that are robust to those types of sample matrices would be helpful.
And then Rick's in here asking, to what level were you able to consistently concentrate the brine?
Yeah, so that was a bit dependent on the feed salinity. So again, quite a bit of variation flex in that raw produced water salinity. So we saw anywhere as low as roughly 30% recovery up to 50% when salinities were on the low side. So really, it does kind of speak to the flexibility that a commercial system needs to have built into it to accommodate for those changes in feed salinities. On the thermal desalination side, that's not really as much of an issue as it's less prone to changes in that feed salinity since you're just basically increasing the amount of time that water remains in that recirculation loop for the desalinator, the thermal desalinator. Whereas with the membrane system, you have a fixed amount of surface area, so you really can't desalinate further if your salinity increases. Like you just run out of surface area out of membranes.
Yeah, that makes a lot of sense. Couple other questions floating in here. Someone might have missed it, but where was the site of the pilot located again?
So it was in the Permian Basin, just south of the Texas-New Mexico border. So really close to Red Bluff Reservoir, if you're familiar with the area.
Thank you. And then Jonathan Michelson from Sun Vapor was asking if you were able to share any details on membrane cleaning approaches that were helpful to reverse organic fouling.
Yeah, we've done a lot of work on that actually. I'm not sure how much I can share here, but yeah, happy to talk offline.
Very good. Anything else you guys want to add before we close out here? We just made it to the end of our Q&A.
No,
Any
just thank you again to the consortium and to everyone here for the questions, and very glad to be able to speak to everyone today.
I think the pleasure is all on our side. So you are the ones that make our webinar series possible. You guys are out there doing all the hard work, spending all the money, and so we really appreciate it and um, letting us be involved with your projects to the extent that we have been. So really, really appreciate it. And with that, I think we'll wrap up. And so one more big thank you to Javier, Mohammed, and then Western for all that you guys do. So appreciate it. And we will see everyone next month. Take care.
Thank you.
Thank you.